one of the reasons we wanted to look at center of mass is it actually starts, it'll come back to this problem, but we had looked at collisions in 2D, and we had looked at conservation along each of the orthogonal axes. So we had said basically conservation of momentum holds as a whole, but it also holds, because of the independence of orthogonal components of motion, it means that you can independently say that no matter what direction it's moving in, the x components of the momentum have to be conserved independently of the y and independently of the z. Okay, so that means that we can take this two-dimensional problem and break it down into two one-dimensional problems, right? And that allowed us to say, well, if I have a block moving to the east and a block moving to the north, one of them has x momentum, the other has y momentum, and not any of the other, right? So I can easily calculate the total x momentum. It's just the one that has the x. Total y momentum is just the momentum of the one that has the y. And in the final state, after they stick together, that combined mass still has to have this much x momentum and this much y momentum. So I've basically worked out what the components of the two are, right? And then I use Pythagorean's theorem to get the total magnitude of the combined momentum and the arctangent to get the angle. Okay, so, and we will come back to this in a little bit. I think we kind of went over this one as well, where they came in at two different angles, and then we just had to decompose this one into an x and y each. Right, so now they both blocks have an x and a y, but you just add up the x's and you add up the y's. And in this case, it turned out that the y's canceled each other, but the x's added together. Okay, and then we moved on to center of mass. So, oops, sorry. So we talked about center of mass as being the point. One way to think about it is there's a point in any oddly shaped mass where if I manage to put my pivot point, like a little apex, underneath that point, and I'm just careful enough, I can get it to balance on that point. You see these rock balancers do it at the beach all the time, right? And mathematically, the way we get at that, finding that center of mass, that point where the mass is evenly distributed about that point, is we take the distance-weighted mass, or I'm sorry, the mass-weighted distance. Same thing, actually. Right, so instead of taking instead of just summing up all the distances or just summing up all the masses, what I'll do is I'll go along and I'll break apart my whatever object it is I'm trying to find the center of mass of, and I'll say how much. I'll find a zero. Let me call this the zero, right? And I'll say I'm going to slice it into a little slice here. How much mass does it have, and where's its average position? It's right here. We'll call that 1. 2 centimeters away, there's also another slice that has the same mass, 3, 4. And if we do this for a uniform rod, then it just comes out right in the middle, right? But if it turns out that we have something heavy at the end, right? We put something heavy at one end, right? Let's say this is a big heavy metal ball, then the center point will actually be here, because when you add this little slice here, this comes in with a lot more weight, right? No pun intended, but it's weighted heavily, right? Because it's got large mass. Okay, and so that procedure is just what's described mathematically here, taking the sum of the mass of each little slice times the position of each little slice, add them all up, and divide by the total mass. And we can do that in x, we can do it in y, we can do it in z, and then we'll have the x, y, and z components of the center of mass. If we're working in something like spherical coordinates, or x, y, and z is just not the relevant coordinate system for us, we can summarize this a little more easily as just saying MIRI. So you'll see that's in your textbook, where R is just kind of a radial directional unit, right? But you're basically again taking what the position is of this little elemental piece of mass, and how much mass it is for that elemental piece of mass, and summing them all up, and then dividing by the total mass. Okay, so we'll look at some examples. Right, if I have these 3 point particles, right? If I just tell you I've got 3 balls of different masses, and I'm just going to place them down, and I want to know what is the center of mass of this system of 3 masses, right? Well, all we do is we just take, to find the x, first we define an origin. We define some place we're going to call 0. We'll call this point 0 right here. And we're going to take the sum of each mass times its x position, just its x position. Right, so that means, first of all, we're going to divide that by the total mass. The total mass is just the three masses combined, 10, 20, 30. But for the sum, we have the first mass is 10 kilograms, and its x position is over here at -1. I look at mass 2. Its x position is also -1. It's a different y, but we don't care about that right now. And then I say mass 3, that's 30 kilograms, and I'm going to times that by its x position, and that's at +2, 1, 2. Right. And if I do that math, I get -10, -20, plus 60, which is 30 over 60.5. So the x-coordinate of the center of mass is at 1/2, right here, somewhere along this line. Now we got to find the y center of mass. Do the same thing. Total mass is the same, 10 plus 20 plus 30. Each individual mass, M1, again, 10 kilograms. This time, it's at +1y. The 20 kilogram mass, M2, is at -1y, right? So it's down here at -1. And the 30 kilogram is at +1. Right, so that's +10 minus 20, which gives me, I think, -10. And then I add another +30, and that's going to give me 20 out of 60 is 1/3. Okay, so he's down here a little below half. So at 1/2 and 1/3, that's the center of mass. And as I mentioned before, the center of mass does not have to be where there's actual mass, right? I take a curved thing like this, the center of mass could very well be right here, right? In the case of these three particles, it's just floating somewhere in space. But if you think of these as a bunch of heavy metal spheres, and I again, glue them onto a piece of cardboard, then this is where I would want to stick my finger underneath that piece of cardboard so the whole thing would balance. Right? If you've ever done any waitering or waitressing, you're very familiar with this idea. Right? Add another glass here, and you're going to have to shift over a little bit or move your fingers. Okay. Now, that's if we're taking like individual particles, right? How do we find the center of mass for something that's a solid thing, right? Well, let's start with something very easy, like a cube. Right? It's pretty obvious, I think, if we think about it, that the center of mass of a cube of uniform material, like it's just solid aluminum, is just going to be the exact dead center of that cube, right? But let's verify that mathematically. Right? So the mathematical process is that we can divide this into, we can take our cube. Do I have a cube? Oh, I left my cube. I have no cube. This is my cube. So we take a cube, and we divide it up into little tiny bits, little slices, and we take each one of these slices, take its mass, take its position, sum it up. But to do it as accurately as possible, we want to take these slices as thin as possible, in case there's any variation, and it turns out that there's any variation in mass. We want to be able to catch that. And so the limit of that fine slicing is an integral, right? So the center of mass, instead of taking a sum of x's times the little mass over the total mass, we take an integral x dm. Okay? Take the position and a differential amount of mass, just that little slice of mass, and the x position of that. So let me see. So let's write this out. We know that we can divide the block into a series of these thin slices. Each of the thin slices will have a volume of w by w, right? So imagine this is a solid cubic block, right? It has a certain width, a certain height, right? But I'm only going to take a tiny slice of it. So it's w by little delta x, right? And so the mass is going to be given by the mass density of this thing, how dense it is, times that little sliver of volume, right? Which works out to be rho times w times delta x. And again, we've defined the volume as the mass per unit volume. And if we take this to be an infinitesimally small slice, not delta m, but dm, then we just replace the delta x with a dx. So we have rho w squared dx, and that's what we're going to plug into here. Right? Our dm becomes rho w squared dx. So I have x rho w squared dx. I've got an x dx over here. And when I integrate x, I get x squared. right? But the half comes down, because remember, if you differentiate this, you would take the exponent, you bring it down, so that 2 would cancel the 1/2, and this would go down from a 2 to a 1, and you would just end up with x. Okay. So we evaluate that from w to 0, and we see that this comes out as, at the w side, it's 1/2 w squared, and at the 0 side, it's just 0, so we subtract 0 from this, and we are left with this expression. These cancel, and we end up with w over 2. Right? Okay, and so that makes sense. The x center of mass is exactly halfway along the block. We can do the same thing with y and z and get all the same stuff. Right? So that was really quick, but it was really easy. But that is the process by which you're going to find the center of mass of something that may be non-uniform. Right? If we had something, and I don't think I assigned any homework, but where they give you a formula for the mass, right? They could say the mass varies as ax squared plus 3, right? So then you'd have to take the integral of that or take the derivative of that as necessary. Right? W is the width of the block. I'm sorry, I didn't define that very well. So if I'm taking a square block and it has a width of W, right, what I'm doing is I'm saying that if I take a slice through this block, right, imagine this is a perfectly cubic block. I forgot my cube, right? Then it has a width, that little slice that I'm taking, I'm cutting these up into little slices of cheese. Every slice of cheese is going to be W wide, W tall, right, but only delta X thick. Right, so then the volume of each of these little tiny cheddar cheese slices is W squared times delta X. Okay, so that's the volume of each slice. All right, so what would we do if we had something? Let's take a baby step into non-uniformity, right? And say we have 2 uniform blocks placed side by side, and they're glued together. Right, so now I've got a block of styrofoam and a block of steel. And I glue them together, and I ask you, where do I put my finger underneath this double block so that it balances? Now, intuitively, you should know it's going to be towards the heavier side, so the answer should be that, right? You know you're not going to put it, if you put a block of styrofoam here and a block of steel and glue them together, and you put your finger right under the midpoint, you know the steel is going to go roomp, right? So you're going to have to move over probably close to the middle of that steel ball, right, or that steel block, if the styrofoam one is very, very light by comparison. Here, it's not quite so different in mass. It's not quite styrofoam to steel. One is 3 kilograms, and the other mass is 1 kilogram. All right, so let's figure out where the center mass of the glued combined blocks is. So for the solution, we previously found that the center of mass of each uniform square block lies at the exact center. Right, so the center of mass of the red block is going to be at 0.5, 0.5, 0.5, right, or minus 0.5 for the x, but it'll be at plus 0.5 and plus 0.5 for y and z. The green block will be at plus 5, plus half, plus half, plus 1/2. One trick here is that I mentioned at the end of last class that once we found the center of mass, we can attribute the mass, we can attribute all of that mass as if it were sitting at this one little infinitely thick, infinitely dense particle, right, for the purposes of non-rotational dynamics. So we attribute the full mass of each block to its respective center of mass, and then we can find the center of mass of the glued double block by the same method we did for that very easy problem here. Right? We're basically saying this actually represents a gigantic block, and this actually represents a gigantic block, and we just glue them together. Right? So all we have to do is now take 1 over the mass times the sum of these, and there's only 2, mass 1 and mass 2, and we're going to use the center of masses of each one of those. Right? From symmetry, we can kind of guess that it's, where it is in y and z. Right? So it really is a matter of just where is it in x. Right? Because these two things, I have these 2 blocks that are uniform in x and y. So you can imagine if I tipped it on one on top of each other. So now I've got a steel block and a styrofoam block right on top of each other. The center of mass is just going to be the center, right? So the only thing that matters is the center of mass in the direction where I have non-uniformity, in the x. So in that x component, I say, well, I know that I have a center of mass over here at minus 0.5, and I have another center of mass over at plus 0.5. One has a mass of 3, one has a mass of 1, and so I end up with minus 1/4, right, which tells me that it is over closer to the red block because the red was negative x. Right, so over on the negative side. And the red block was the heavier one, so that all makes some intuitive sense. All right? So good. That's how we calculate things for center of mass. So if I give you different blocks, different rods, you now know how to do it. Why are we bothering with all of this, right? I mean, this kind of seems like an aside. All of a sudden, we're talking about center of mass when we were talking about collisions. But what's nice about center of mass is if you have an isolated system, right, then total momentum is conserved. So that means the total momentum of the system is conserved, but if the system started off as 3 different things and then ended up being one thing or 2 different things, that's a little hard to say. It's kind of hard to track, right? But what we can track is if we think of those 2 objects as one object that has a center of mass, right? Remember when I had this thing, I could pretend all of this mass was right here, right? So I could just treat that as a particle, right? Similarly, if I broke this into a bunch of little balls, I could say all those balls actually act like it's one ball right here, as long as they're glued together. So if I just had 2 balls, or 2 blocks, I can still treat that as, that's one object. It's just kind of a separated object, but it's one object. Where's its center of mass, right? Well, we just did that. We figured out, if I have a point particle here and point particle here, I can figure out the center of mass for the combined set of particles, 2 or 3 particles. So when we had this collision that came in, one coming to the north and one coming to the east, we found that they stuck together and they went off at some angle, right? And we calculated that by looking at the individual components. But another way to look at it is that since there's no outside forces, it's sliding on a frictionless surface, and we're looking at these 2 blocks that come in and go out together, right? As long as we include both of those blocks as our system, there's no outside forces, so the momentum should not change, right? That's what it means for momentum to be conserved. The momentum before and the momentum after have to be the same. So if I define my system before as the 2 not yet combined blocks, but I consider that one system, and then I consider the block afterwards as one combined block, its momentum can't change, right? So if I say all that mass is concentrated here, how's it moving? Well, if we look and say it's going to do like this, combine, go back, and then I trace it backwards, right? Just before the collision, this one would be here, right? Because it has a velocity of 1. This one has a velocity of 2, so it's actually down 2 ticks. 2 seconds before, it's down here, 4 ticks, then 6 ticks. This one's down back 1, 2, 3. If I draw the line between them, right? Because if I have 2 masses, the center of mass, if I attach these with a really, really, really fine rod that has almost no weight, then clearly the center of mass that I can balance it on has to be somewhere on that rod, right? This is the line connecting the 2 centers. It wouldn't be way back here or anything weird like that, right? So the center of mass has to be somewhere along here, right? And if you do the calculation, it'll turn out that it's right here, and right here, and right here. And then if you look at it, if you just treat the entire system as one object, that object went undeviated even through the collision, right? So that's a really nice way of looking at conservation of momentum. That when you have an isolated system, the momentum of the entire system as a whole just doesn't change, right? We're used to kind of think of it as before and after, and we kind of think of it as a change, but it's not really. The momentum of the whole system stays the same. Okay,